In this problem, we want to look at this compound here, so the dimethyl substituted cyclobutane, and figure out exactly how many proton NMR signals we would expect to see. And sometimes in compounds like this, it's a little bit tricky to just look at it and figure out the number of chemically equivalent or chemically different hydrogens. So what we're going to use is sort of a test for chemical distinction or equivalence. And the way this works, so we'll draw two versions of the molecule, and each will have one of the two hydrogen in question replaced with an X group. And then we're going to look at the relationship between those two compounds. So if they end up being identical or enantiomers, then those two hydrogen that we replaced are chemically equivalent, and they would show up as a single signal on the NMR. If the two compounds are constitutional isomers or diastereomers, then those hydrogen are chemically distinct and would show up as two distinct signals on the NMR. So we're going to work through this for this compound above. And one of the first things you might want to do is just draw this molecule with all of your hydrogen atoms drawn out, so that you can easily visualize everything that's in the molecule, and we'll see what we need to replace as we go through this. So we'll just start with our methyl groups. So are the hydrogens on the methyl groups chemically equivalent or chemically distinct? So we'll draw two versions of the molecule. In the first version, I replaced one of the hydrogen in this methyl group with an X. In the second version, I replaced one of the hydrogen in the other methyl group with an X. Okay, and we know for this methyl group, all three of those hydrogen are equivalent, so we won't deal with those. But we're comparing the hydrogens in these two methyl groups. So now if we look at these two compounds, and we want to think about the relationship, well really if you just take this compound on the right, flip it over horizontally, you'll see that you can superimpose it right on top of the compound on the left. So these two are identical. So remember, if they're identical, that means the hydrogen on this methyl must be equivalent to the hydrogen on that methyl. So we'll label these as proton A. Okay, so that would be one signal from those two methyl groups. Okay, so from there, now let's move on and figure out whether these two hydrogens are chemically equivalent or chemically different. Okay, so here I have drawn out two molecules. In one I've replaced the hydrogen on the left with an X. On the other I've replaced the hydrogen on the right with an X. So once again, if we look at these two, you can think about taking this compound on the right, flipping it horizontally, and it would superimpose right on top of the compound on the left. So once again, we have an identical set of compounds. So that means this hydrogen and that hydrogen are chemically equivalent, so they would show up as a distinct peak. So we'll label those as B. Okay, so from there, now we'll move on and let's think about these two hydrogen on that CH2 group. Okay, so it's easy for people to want to say, well, these two hydrogen are on the same carbon. They must be chemically equivalent. But are they really? Well, let's take a look at it and see. Okay, so here I've replaced in one molecule the back hydrogen with an X, and then in the other representation the front hydrogen with an X. Now if we look at these two compounds, they're not mirror images, they're not identical, and they're not superimposable. So there's no way for me to set this compound on the right down on top of the one on the left, because essentially I have a hydrogen out, a hydrogen back, they would bump into one another. So these wouldn't line up. So these two must be diastereomers. So if they're diastereomers, that means that these two hydrogen must be chemically distinct. So they're different. So we've already used A and B, so I'll make one of these hydrogen C, the other D. So those would show up as two distinct signals. So now let's think about comparing maybe this hydrogen that's pointing out on this side with the hydrogen that's pointing back on this other side. Are those chemically equivalent or distinct? So once again, this hydrogen that we've already labeled as D, I'll replace with an X, and then this hydrogen on the back carbon, I'll replace that with an X, and we'll compare those two. So now, in these two, if you think about taking this compound on the right, flipping it horizontally, this would superimpose perfectly with the compound on the left. So these two are identical. So that must mean this hydrogen pointing out is equivalent to the hydrogen on the other side pointing back. So if this is hydrogen D, this hydrogen must also be D. And then by virtue, it's going to be the same thing for C. On this side, the one that's pointing back is equivalent to this one that's pointing out. So we've essentially have our whole molecule assigned at this point. But just for sort of one last confirmation, let's go ahead and confirm that hydrogens C and D are distinct, or if you think about it in the other sense, that C and D are distinct. So we could consider the C and D at the back or the C and D on the front, and for this example, let's just compare the relationship between C and D on the front carbons. Okay, so we'll draw two molecules replacing each of those with an X group. Okay, so here I have C replaced with an X, and then this D replaced with an X. So now we're essentially dealing with these two front protons. And if we look at these two and try to figure out what the relationship is, well, they're not identical. They're not mirror images. They're not superimposable. So those must be diastereomers. So that means that the two protons pointing out on the front are chemically different, and we've already confirmed that. We can see that C and D are in fact two different signals. So now, if you think about this compound, we've identified A, B, C, and D. So this would show 4 distinct proton NMR signals.